Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. Let's continue the second topic of the second chapter on Fourier series. So the outline for this second topic is the trigonometric form versus the complex exponential Fourier series, and the second part is Parseval's theorem. Okay, I believe that you have seen this kind of equation in your first year courses, either in mathematics or in other subjects, in which when you have a signal, a periodic signal like this, so you can write the equation for the given signal by using the general form or trigonometric function, in which you need to identify the coefficients a(n) or b(n), and also you need to determine the sequence and based on the number of harmonics. On the other hand, you need to compare the property of the signal. If, for example, the signal is even symmetry, then certain variables will be 0, so that you can simplify the overall derivation. Okay, these are the example when you have even symmetry signal, so that by comparing the property of even symmetry, Bn will be 0, so you just need to solve for An and solve the integration. So this is one of the example conventional method to determine the Fourier series of the given signal by using the integration and comparing the property of the signal given. Okay, in this course, the Fourier series can be represented simply by using a Fourier coefficient table, in which you will be having the coefficients C0, Cn, and C minus n from the table. Then you can derive the equation for complex exponential Fourier series. Okay, so from the table you will have specific equation for the coefficient C0 and Cn based on the shape of the signal, and the equation can be further simplified into this form. Okay, C0 is the constant or DC values, and Cn is the coefficients of your Fourier series. Okay, so this is a step to derive or to write down the complex exponential Fourier series for the given signal. For example, you are given this particular signal, so you need to compare to the Fourier coefficient table what types of signal is this and what are the parameters or variable involved. So please take note this equation. This is very important so that you can write down all the variables needed in your calculation. So the first step, when you are given a signal, so you need to refer to the table for the coefficients values C0 and Cn, and you need to compare the given graph with the graph in the table, and you need to determine all parameters included, as for example the x0 and the t0. Next, you need to calculate the Cn values based on number of harmonics required, both the positive n and negative n values. Lastly, you can write down the complete complex exponential Fourier series up to the number of harmonics required. Okay, this is how the Fourier coefficient table looks like. So please bear in mind this general equation for complex exponential Fourier series. So from the table, you may notice there's a column for C0, okay, in which this C0 in the equation will be replaced by whatever equation appeared in this column, depending on types of signal you have. And next column is the Cn equation, again based on types of signal you have. And the last column represents the remark for each particular function. For example, for the first one, square wave, so Cn will be 0 when n even. So this Cn will be 0 if n even, so that you just need to consider the odd number. So for example, you are given this signal, so you need to compare to the table the closest shape to the signal given to you. So in this case, the closest one is the triangular wave. So from here, you know that the C0 for this particular signal is x0 over 2, and Cn is negative 2x0 over pi n squared, and that's a remark for this particular signal. And you should also take note the variables involved. So in this case, x0 equal to 2, and the t0, the fundamental period, equal to 20, and don't forget the unit millisecond. Okay, let's try this example. You need to write the complex exponential Fourier series for this signal xt for up to third harmonic. Third harmonics meaning that n up to 3. So you need to consider all values from n equal to 0, n equal to 1, n equal to 2, n equal to 3, both positive and negative values. Okay, so the first step, refer to the table, look at the suitable function. So in this case, it is triangular wave. So then you need to identify the parameters from the table. So in this case, x0 equal to 2 volt. So x0 equal to 2. And then your t0 is equal to 20 millisecond. So your t0 is 20 millisecond. So from t0, you can calculate your omega naught, in which, or you can calculate your f0 equal to 1 over t0. So from here, you can get your omega naught equal to 2 pi f0, in which it is equal to 2 pi 1 over t0. So in this case, your omega naught equal to 100 pi. Okay, next, write down the general equation, C0 plus the summation of Cn, Ejn, omega t. So replace the C0 and Cn equation based on the equation shown from the table. So in this case, for triangular wave, the C0 is equal to x0 over 2. So your x0 equal to C0 over 2, and your Cn is negative 2x0 divided by the function. Okay, so please don't forget to look at the remark. So Cn will always be 0 when n even number. So the question asks you to get up to n equal to 3, but Cn will be 0 when n even. So you just need to consider the odd number. So you don't need to consider n positive and negative too. Okay, from the previous slide, we know that your x0 is equal to 2 and your t0 equal to 20 millisecond, and from your calculation, omega naught equal to 100 pi radian per second. Okay, so from the general equation, so this is your C0 plus summation of Cn, Ejn, omega t. So you can replace your omega with 100 pi. So then you replace x0 with 2. Okay. And then you just need to calculate Cn based on the n values. Okay, since the question asks you to consider n up to third harmonics, so in this case, you need to consider n equal to 1 and 3, and also -1 and -3, both positive and negative values. So then this is the Cn. So Cn equation is, this is Cn equal to -4 divided by pi n squared. Okay, from here. So you then calculate your Cn. So if n equal to +1, okay, so you replace the n with +1, so you get this equation. Then go for n equal to -1. So when n is -1, so you get this for C -1. Next, C +3, replace n with +3, so you get this equation. And for C n equal to -3, replace n equal to -3, so you get this equation. So last step is to write down the complete Fourier series equation in exponential form. So remember, the basic equation is C0 plus the summation of Cn, Ejn, omega t. Okay, so this is your C0. So this is your C0. Okay, plus C1. So this is your C1. Supposedly plus, but your C1 is negative. So this is your C1, +1, C1 Ejn. So n equal to 1 in this case. So that's why Ej 1 times 100 pi t. Okay, and then plus C minus 1. So this is C minus 1. This is when n equal to -1. Okay, plus when C 3. Okay, so in this case, n equal to 3 times your omega 100 pi. And this one when n C minus 3. N equal to -3, so it's -3 times 100 pi. Okay, next you can simplify this equation. So group the same coefficient value. So in this case, and this is for omega 100 pi and omega 100 pi. So this is the coefficient. So this is for the next omega values. Okay, so then when you have, remember, in trigonometric form, when you have negative, you can convert them into positive values by having a phase shift of positive pi. So all negative being converted into positive by having phase shift of pi inside the bracket. Okay, so finally you can plot the spectrum, both the magnitude and the phase spectrum. You can look at the first one. You have your C0 here. Okay, so the magnitude is 1, and then the first frequency is 100 pi. Supposedly it's 100 pi here. Okay, so 100 pi, the magnitude is now 4 over pi squared. So same goes to the negative frequency. So next one at 300 pi, so the magnitude is 4 over 9 pi. Same goes to the negative frequency. Okay, next is the phase spectrum. Okay, so at 100 pi, positive 100 pi. Okay, at 0, the phase is 0. At 100 pi, the phase is positive pi. Here, this one. At negative 100 pi, it is negative pi, this one. So at positive 300, it's positive pi. And at negative 300, negative times positive is negative, so it's negative pi. So this is negative pi values. Okay, so that's the amplitude and phase plot for the given function. Okay, let's look at the second example. So you are given these signals, then you need to write down the complex exponential Fourier series equation of yt and sketch double-sided spectrum. Okay, so ignore the question C for a while. So we're going to discuss this in the next session. Okay, so first step, always refer to the table. Refer table. Okay, look at the more or less similar shape and identify what is the x0 and then t0 and then c0 and also cn, and don't forget the remarks. So in this case, your x0 equal to 6. So x0 equal to 6. What else? The t0 equal to 1 second. So t0 equal to 1 second. So f0 equal to 1 over 1. Okay, so then your omega naught equal to 2 pi, f0 equal to 2 pi. So this is your omega naught. So what else? You have the C0. This is your C0, and this is your Cn. And no remarks. Okay, no remarks. So all n values need to be included up to third harmonics. So don't forget the general equation. So in this case, it's yt equal to C0 plus the summation of Cn, Ej, and omega naught t. Okay, so you already know your C0 equal to x0 divided by 2 plus the summation of all n from negative infinity to infinity except n 0, because this is for n0. So your Cn is j x0 divided by 2 pi n. So this is your Cn. This is just the Cn. Don't forget the rest of the function e, j, and you can put your omega naught 2 pi t. Okay. Okay, this is the general equation. So as shown in the earlier slide, so this is your omega naught equal to 2 pi. So you can replace all the x0 and cn equation and also your omega values. Okay, in this case, your x0 is 6 divided by 2. This is your cn equation. So x0 is equal to 6 divided by 2 ej, and so replace omega with 2 pi. Next is to identify the Cn values up to third harmonics. So up to third harmonics, you need to consider all n negative and positive 1 up to 3. Okay, so for n equal to 1, so replace the Cn equation. So Cn equation is Cn equal to g x naught divided by 2 pi n, 2 pi n. Okay, so when n equal to 1, so replace n equal to 1. So j, okay, for j, when you convert it, when if you want to remove the j, it is basically equal to the phase shift of pi over 2. Okay, so go next for n equal to minus 1, replace n minus 1. So again you have negative j, so you convert it into negative j pi over 2. Okay, same goes to the rest of the n. Okay, lastly, you need to write down the complete exponential Fourier series for sawtooth signal. So this is your C naught plus the Cn. Okay, C1, when it is C1, the coefficient is 3 over pi e j n omega naught t. So this is omega naught. So this is when n equal to 1. So this is the part of the coefficients because of the j just now. Okay, so same goes to when n equal to minus 1. So this is n equal to minus 1 times omega naught t. Okay, and this is for n equal to 2. So n equal to 2 times 2 pi. So this is when n equal to minus 2 times 2 pi. And this one for the third n times 2 pi. And last one, negative 3 times 2 pi. Okay, once you have complete the equation, you can simplify the equation by group them based on the frequency. Okay, so this is the C naught, this is the C1, both positive and negative values. Okay, this is when you have positive frequency. Okay, positive frequency, and you have positive phase shift. When you have negative frequency, you have negative phase shift. So negative times positive, it's negative. Okay, and so you can notice that inside the box, okay, inside the bracket, always similar. Okay, for all cases. All right, and this one as well. Okay, so same goes to the when n equal to, this is for C2 and this is for C3, both positive and negative frequencies. Okay, so lastly you can plot this amplitude spectrum and phase spectrum. The first one is when C0, the amplitude is 3. When C1 at frequency of 2 pi, magnitude is 3 over pi, this one. Okay, at positive frequency, at negative frequency, same magnitude. Okay, same goes to the second one and the third one. And then plot the phase spectrum. Okay, so at C0, no phase, so it's 0. Okay, at positive 2 pi, the phase is positive pi over 2, this one. So at negative 2 pi, the phase is negative pi over 2, this one. Okay, same goes to the second and the third one. So you have completed the equation and also the complex exponential equation and also the double-sided spectrum for the given signal. Okay, how about when you are given an amplitude and phase spectrum, but you need to write down the expression in trigonometric form? and then you need to sketch the single-sided spectrum. So currently you are given double-sided spectrum for both the amplitude and phase spectrum. So meaning that from the spectrum, double-sided spectrum, you know you will get exponential Fourier series. Okay, so therefore in order to get trigonometric equation, you need to convert the exponential Fourier series into trigonometric function. Okay, so to start with, you need to write down the mathematical expression in any form that you can get from the graph. Obviously, this is the double-sided spectrum, so you can get exponential Fourier series. Okay, start with C naught. So C naught equal to 3 plus C1. Okay, C1 EJ omega naught. For the first one, positive omega naught. Okay, so this is omega naught, and then the phase at 2 pi, it is positive pi over 2, so that's why it is positive pi over 2. Okay, plus the negative frequency at negative 2 pi, the magnitude is still 3 over pi, same magnitude. And look at the phase at negative 2 pi, it is negative pi over 2. So it's still pi over 2, but you need to check the polarity. So in this case, it is negative pi over 2. So make sure the multiplication will produce negative pi over 2. Okay, move on to omega equal to 4 pi. So now the magnitude is 1.5 over pi. So for positive frequency 4 pi, and negative frequency is supposed to be 4 pi here. Okay, so same magnitude for the second one, and then look at the phase. At positive frequency it's positive pi over 2, at positive frequency it's pi over 2, at negative frequency it's negative pi over 2, at negative frequency this one, so it's negative pi over 2. Okay, move on to the last pulse at 6 pi, positive 6 pi, the amplitude is 1 over pi. Okay, so positive and negative 1 over pi, the coefficient or the magnitude, and check the phase spectrum. Okay, at positive 6 pi, so it is positive, and at negative it is negative. Okay, so you already have the exponential Fourier series in hand. So from this exponential Fourier series, you can convert this equation into trigonometric form. Okay, from the previous slide, this is the complex exponential Fourier series. So then you can convert this exponential into sine or cosine function. Okay, so remember, if you have cos omega naught t plus theta, so in exponential form it will be e j omega naught t plus theta plus e minus j omega naught t plus theta divided by 2. So you can group your exponential equation based on this general equation. Okay, so in this case, to get into this shape, so you already have 3 over pi, so how to make it into this? Okay, so you need to divide by 2. Therefore, in the original equation, there's no division by 2. So in order to to get it being divided by 2, so you need to multiply here by 2. Okay, so same goes to the second component and the third component. So the equation already in cosine shape, but still in exponential form. Okay, so now you convert everything into cosine function. So this is already in cosine function. Okay, so this the second component, and this is for the third component. Okay, so 6 over pi. So this is whatever inside the bracket. Okay, this is for the second component and the third component. So you already have the trigonometric equation. Okay, lastly, you can sketch the single-sided spectrum from the trigonometric equation. So this is your C0, and then you have your first spectrum at 2 pi, positive 2 pi, and at 2 pi the phase is positive pi over 2, this one. Okay, same goes to the second and the third one. Okay, so that's it for now. So I'll see you in next session. Thank you.